In this video, I want to talk about what's called the null space of a matrix. Here, we're going to start with the matrix A, which is just 1, 2, 3, 4, 5, 6, 7, 8, 9. This is one that we've worked with before. In fact, we've seen that if we apply elementary row operations, we can get this into a reduced row echelon form where it's 1, 0, minus 1, 0, 1, 2, 0, 0, 0. So that's the reduced row echelon form of our matrix A. And what I'm going to do with this matrix here is, and this works with any matrix, it does not have to be square. Um, what I want to do is I want to consider the set of vectors x in R3 such that a times x is equal to 0. So remember that this is a notation that I've used before, but this means that x is an element of R3. So that's just a nice way to represent that. And what we're going to do with that is I want to think about all the x's so that a times x is equal to the 0 vector. In other words, what I want to do is I want to solve the system. I want to solve, this is equivalent to solving 1x1 plus 2x2 plus 3x3 equals 0, and 4x1 plus 5x2 plus 6x3 equals 0, and 7x1 plus 8x2 plus 9x3 equals 0, right? So really I'm just kind of going backwards, but we want to look at what's the set of all the vectors in x3 where a times x is equal to 0. And again, that's equivalent to solving this. It turns out that this set is going to be very, very important for us. Okay, so that set is going to turn out to be hugely relevant for us. It's got a name. Before I give away the name, let's show a few things about this set. So the first thing I want to do is I want to show that the set of all x values in R3 such that a times x is equal to 0 is a subspace of R3. Okay, so this is going to be a subspace of R3. And so to do this, we just need to apply the subspace test. This is now, and I want to emphasize, what you have to do to start with is you fix a matrix A, pick whatever your favorite matrix is, and then for any particular matrix, you can look at this set. And so the set will change depending on what the matrix is, but once you have the matrix, then this set is well defined. And so the set for whatever matrix A we start with is going to end up being a subspace. And so what we need to do is we need to show that if we add 2 elements in the set, we get another element in the set. And likewise, if we take any element in that set and we scale it, then that's also an element in the set. So let's, for convenience, let's call this set E. And what we're going to do is we're going to pick 2 values, say x and y from E. And then we'll show that x plus y is in E, and that if we scale x, that's also in E. Okay, we're going to be using that is an element of symbol. It just means that it's in the set E. So we have 2 things to show. The first, let's show that the sum of any 2 elements from E is also in E. So let's pick x and y in E. Then the only thing that we know about them is that a times x is equal to 0 and a times y is equal to 0, because they're specifically from this set where that's their defining property. If we add them up, I want you to notice that if I add them up and then multiply by the distributive properties of matrices, this is a times x plus a times y, which is going to be the 0 vector plus the 0 vector, which is of course the 0 vector. And so it turns out that if we look at x plus y, that's also going to be a vector, such that when you multiply on the left of, if you multiply on the left by a, you get the 0 vector. You need to make sure to say that correctly. So in particular, x plus y is in E, and this means that the first step is done, right? X plus y is in E. The second thing we need to do is to show that if we scale any vector x, that's also in E. So our second step, we're going to pick the value x in E, and then we're going to show that k times x is in E for all values k, for all real numbers k. So that's a bold R there for real numbers. So that's our next step. So let's start by pick in x and E. In particular, we know that a times x is equal to the 0 vector. And what that means is that if you were to look at a times kx, what you can do with that constant, and again, this comes down to the axioms that we talked about in chapter 2 that seemed mostly irrelevant at the time, but it turns out that what you can do is you can take this constant k and bring it out front. And in this case, that's going to help us by telling us that we again get the 0 vector. And that gives us the second part, that k times x is also in the set E. Okay, and so these two things together make it past the subspace test. This means that this space is a subspace of R3. Again, it's a very important space called an elementary. It's really called an elementary space because it's so important. And so this is actually called the null space. So the null space of A is going to be the set of vectors x, so that ax is equal to 0. And let me make this a little bit more precise. Okay, so just to make sure that everything is completely clear here. What this is the null space of an m by n matrix A is going to be the set of vectors in Rn such that ax equals 0. So the null space is this set, and then it turns out that this is a subspace. So this is a subspace of Rn, okay, because that's where the vectors live. And I want to write this just a little bit better. Okay, this is how I write my n's, by the way. Sorry about that. Sometimes they can kind of look like u's, but those are n's. So this turns out to be a subspace of Rn, and again, it's a very important subspace. The dimension of the subspace, and some books like to write the null space as null of A. So I will do that as well. So the dimension of the null space is called the nullity of A. And again, once you know that you have a subspace, it's a vector space, you can talk about its dimension, everything is fine. Okay, so that's really all I wanted to say here, is that the nullity of A is the dimension of the null space. The null space is this very important space that we had. And so what we'll do in the next example is we'll take our matrix A that we started with and then actually find the null space for that particular